Hello, and welcome to today's online panel discussion on quantum photonics and how to unlock the new possibilities this technology offers. My name is Mark Elliott. I am the COO of Europa Science, which is the publisher of Electro-Optics. The purpose of today's online panel discussion is ambitious. Quantum photonics is at the forefront of technological innovation, offering the potential to revolutionize computing, communication, and sensing. By harnessing quantum states of light, researchers and industry leaders are opening the door to faster, more secure communications, ultra-sensitive measurement devices, and groundbreaking advances in quantum computing. This session will explore the key principles of what quantum photonics is all about, those recent breakthroughs and emerging applications across a range of industries. And I'm delighted to be joined by four people who are at the cutting edge of this innovative field. First off, we have James Lee, who is the co-founder of Wave Photonics. As well as founding the company, he is now the CEO and undertook his PhD in Toshiba's Quantum Information Group at Cambridge University. At Cambridge, he developed photon sources for quantum computing, followed by a time modeling equity derivatives at an investment bank. James holds master's degrees in photonic systems development from Cambridge University and also physics from Oxford University. Welcome, James. Thanks for joining us today. Then we have Annika Molson, who is the head of engineering at Quantum Dice. Quantum Dice is a venture-backed Oxford University spin-out commercializing the use of verifiable quantum random number generation in cybersecurity and computing. Annika completed her PhD in engineering science at the University of Oxford, where her research focused on optoelectronics and sensors. And prior to joining Quantum Dice, she was responsible for an award-winning VR solution. Thank you for joining us too, Annika. Next, we have Richard Murray, who is the CEO and co-founder of Orca Computing. Richard co-founded the company in 2019. He is an accomplished business executive and technologist with a PhD in quantum atom optics and over 15 years experience spent managing scientific teams who have been working on disruptive early stage technologies such as quantum, but also AR, VR, and other consumer and industrial applications. Orca Computing is growing. It has over 65 people now, and last year established a US headquarters in Austin, Texas. Previously, Richard worked for the UK government, supporting Sir Peter Knight, leading the innovation activities for a £270 million UK quantum technologies programme, and was also pivotal in the early stages of the €1 billion EU quantum flagship programme. Welcome to Richard as well. And finally, last but certainly not least, we have Luca Sapienza. Luca is an associate professor in quantum engineering at the University of Cambridge and Dean, Director of Studies and Fellow at Christ's College. Luca is leading the Integrated Quantum Photonics Research Group, which is based at the Nanoscience Centre. Activities that are overseen there by its research group focus on the fundamental understanding of quantum optics effects on a chip, the development of quantum and nanophotonic devices integrating single photon emitters for quantum technologies, and the study of quantum effects in biomolecules. A terrific team of speakers, I'm sure you'll agree, and a warm welcome to all of you watching either live or on demand later on. These online discussions are designed to be useful and interactive. So if you are watching live, we would welcome any questions from you too. So please feel free to submit them at the bottom of your screens and we'll do our best to tackle them across what I hope will be a very full and lively discussion. Right, with no further ado, let's start with some of the questions. And I wanted to sort of kick off with a fairly general question just to warm ourselves all up. And ask, what are the key benefits that photonics chips and processors provide to quantum technologies? And James, I'm going to start with you because you are the first person I see to the left of my screen. James, over to you.
Yeah, so I'm a believer that, and of course I'm biased in thinking this as the co-founder of a photonics company, but I'm a believer that we can't get quantum technologies without integrated photonics. And the reason for that is, yes, there are other quantum technologies that exclusively use light, but most of the approaches to quantum computing and quantum technology use light in there somewhere, whether it's for trapping or control. And then even the ones that don't use light in there at all, at some point you need to network those computers, and that's going to be with light. And so for all of those, what you need is a way of very precisely controlling light in a compact and scalable way that maybe needs to survive extreme temperatures. And the only real way we know how to do that is with integrated photonics. Integrated photonics is already a proven technology. Yes, there's a lot of changes that are needed for it to be useful for quantum technologies, but really to meet those requirements, I don't see that we have any other option other than using integrated photonics. Bulk optics is good enough for demonstrations. I don't think it's good enough for things at the scale and volume we'd need for a commercial quantum technology.
Okay, so a biased position, perhaps, as you would admit, but is it a controversial one? Annika, let's come to you next. What would you agree with James, or have something different to add?
I'm probably even more biased because we directly use the photonic nature, or the quantum nature of photonics, I should say, to generate randomness. So ultimately, our technology, our architecture relies on photonics per se. And then, of course, moving to photonic integrated circuits allows us to miniaturize, to integrate seamlessly into existing hardware platforms. But yeah, ultimately, we fully rely on the nature of photons to generate true randomness and use these quantum processes to, yeah, then generate keys for cybersecurity, for example. But we also look at probabilistic methods. So we integrate the true randomness, we integrate photonic sources into the computation procedure on the hardware level to directly provide entropy into computational systems. And ultimately, for both of these applications, be it cybersecurity, be it computing, we need photonic shifts because they allow us to generate the randomness at very high speed. And as I said, also to integrate into existing hardware. And specifically for processor architectures, there's probably another point that's quite interesting because using these photonic approaches, photonic ICs, also avoids any crosstalk. And that often inhibits scaling the technology to processor level, what we've seen so far. And I think, James, what you already mentioned is one of the big benefits. We can use existing materials, existing components, the photonic supply chain that is already there without having to wait for new innovation or new ideas, and can already build and scale quantum technologies with existing photonic technologies.
Okay. So I'm going to come back. I've got a couple of questions that are forming, but I want to see whether the panel has a consensus on this. So Richard, I'm going to come to you next to ask that.
I might not help with your consensus. Well, I will partly, but I've got a few things to say. I mean, firstly, I think I'll just answer the question about why photonics in general is good for quantum. So before diving into the chip piece, I always like just suggesting that the reason we're able to isolate quantum and make use of it as we are is because of two core principles. And this is in general not related to photonics. Firstly, you need perfect isolation. So you don't get quantum information if you don't have isolation. And that applies to superconducting qubits. You cool them down to isolate from the environment. Same with ion traps, same with photonics. If you don't have isolation, you get lots of things. You get lots of quantum information mixing with classical, and the output is not quantum anymore. So it's a key ingredient for anything quantum to have perfect isolation from the environment. You also need control. So I always like to say that the contradiction in quantum is to imagine something perfectly isolated, but perfectly controlled. And the control gives you the ability to manipulate your qubits to, for example, carry out quantum computation. The reason to say all of that leading into photonics is there is a massive challenge with this isolation piece. And photonics naturally doesn't have it. So with photonics, you take a single photon, you send it down a waveguide. Very, very unlikely that photon will interfere with the outside environment. It doesn't need to be cryogenically cooled to achieve that, just naturally sort of doesn't interact with much, so it makes it perfectly isolated. And there's a good reason why most of the Nobel Prizes have been first demonstrated using photonics, because it's so easy to preserve quantum information in the way that photonics does. So it's a really great platform for quantum information, long range, ticks all of the boxes. But the challenge comes on this control piece. So the answer to part of your question about integrated photonics and devices in general is you've got light, it's naturally isolated. How do you control, how do you program qubits, in the way that you do? I do think an integrated photonics is part of the answer. So that's my agreement with the rest of the panel. Orca just completed the acquisition of a semiconductor company to do integrated photonics because we do believe that it is the answer. It's really hard. And that excites some of us. It's at the cutting edge of what we can do. But let's be honest, it's really challenged because you need super low losses. You can't lose any photons. You need very perfect control. You need to be able to do what you need to do and perfectly, like with very high fidelities. And on very many occasions, you need super fast speeds. So we're pushing the boundaries of switching speed, for example, way beyond what's possible with telecoms currently. So it's not quite as controversial as I made out, maybe. Mostly agree. The move to chips is really important, but let's be honest, there are some big challenges which we're all excited to be addressing in our work, I guess. But yeah, thank you.
Okay, that's interesting. So, I mean, there's some obvious questions that fall out of that about scalability and the kind of the timing, I guess, of when companies feel confident enough to be able to make those sort of leaps forward and things. But we'll maybe come to that. Luca, what's your take on this? Are you in kind of agreement with the broad consensus or not?
Well, I mean, linked to what Richard was saying, of course, I mean, one of the good sides of photonics is that you have very weak or no interaction when the photons are propagating, but it's also one of the challenges because if you want to make operations with these photons, we need to increase light matter interaction and, for instance, create optical cavities or waveguides, resonators. So this is something that we can do with integrated photonics. So I would say photons gives us speed, of course, and low or no interaction, so ability of propagating without being perturbed, potentially low power consumption, and but then developing the chip technology is what allows us to miniaturize all this, so have a small footprint and something that can potentially be used in devices. And I would say that like one of the great advantages of integrated photonics is that the fabrication processes are compatible with the existing technology. So we might think that like we don't need to revolutionize completely our fabrication line or industries in order to be able to fabricate devices that were probably developed already in a different way for classical photonics and now can work down to the single photon level.
And in terms of, the challenge then for organizations wanting to move into this space, I mean, how, if we were having this conversation a couple of years ago, do you think the broad consensus about the timing and the fit would be the same, or is this a rapidly evolving kind of context where actually people are getting more or confident because there is progress, or is it still, something that a lot of people feel quite nervous about? What's the sort of view from the panel on timing of this? Richard, do you want to go?
Yeah, I can kick us off because actually, as a company, we spent a long time deciding to get into integrated photonics. And okay, in the end, we did so by acquiring a company, so quite a big move. But I think, I'll be honest, I think it is quite hard to really properly make the move into integrated photonics. It takes a lot of money and investment and time to develop the platform, especially to do what we're trying to do, to deliver devices with low losses. We spent a long time working up partnerships, considering capital investments. And let's be honest, like if you actually want to buy the hardware to do this, that is a huge decision stroke risk for any company. So there are important considerations that I think make it not trivial how you approach integrated photonics. And I guess other people on this panel will have different sort of services they provide to do that.
Yeah.
In one particular thing, I also wanted to add that I see a lot of exciting progress within integrated photonics. So particularly Orca's platform is tracking, we have a silicon nitride platform that's got really low losses. Question is, how do we achieve the super high speed switching that we need without impacting the losses? And now there's this amazing emergence of integrated lithium niobate, so electro-optic materials on top of silicon nitride. That I think is very recent. It's been around, people have known about materials for a while. Can you do it properly with the scale and the quality that you need? I think that's only recently emerged in the last 2 years, if not a year or 6 months ago, and we're all racing to do some of that. So I think there are some really exciting developments from my perspective that are happening, which make it really exciting to be involved in at this point.
Okay. Annika, I was going to ask you, if I may. I mean, the losses issue is obviously something that we all recognise that, you know, is an inhibitor to its effectiveness. What's your take on how you have kind of addressed that challenge?
So for us, losses is probably not even the biggest concern, because ultimately what we do is generate randomness. So it doesn't really matter if the next sample is the previous one or not, because they are inherently independent. So for us, losses is not the biggest concern, unless we talk about, of course, energy savings, efficiency, all of these parts. But a loss in the photonic part is not as critical as it would be in computing and so on. So we have a bit more flexibility on this one. I think challenges we saw when we moved to photonic integrated circuits was, of course, long lead times. As a startup, this is, I would say, it's a different time frame to what we usually work with. And of course, we had to go and de-risk by doing discrete photonic approaches in the meantime. But yeah, long lead times, high upfront costs, and I think for our use case, laser integration. So not all material platforms allow this, of course. And then it's also about scalability and repeatability. So for us, having moved from proof of concept to then large-scale systems and development, we need the really consistent and repeatable fabrication and manufacturing techniques and control of that as well. And I think with new materials coming in, new technology platforms, this is something, yeah, we are closely monitoring and collaborating with. And for us, the big question is always, where would we hit bottlenecks in scaling and in volume production? Because if we realize much later on, we might need to redesign something because we have made this based on proof of concept designs or something, that will be a big problem later on. So from the very first designs and very first prototypes, to always think about, okay, where could we hit potential bottlenecks in the entire supply chain, in all of the testing processes, in the control methods, and so on. And I think that was one of the challenges for us in moving to photonic integrated circuits.
Okay. And James, I was going to ask you then, you know, in terms of identifying bottlenecks before you hit them, I mean, is that something that you have perfected, a sort of a method to kind of smooth out that kind of runway, or are you still kind of finding things that you weren't expecting as you work on projects?
If I can answer the question before first, which I think is also very interesting, the one that Richard answered. One of the big like exciting shifts that I think moves the whole space forwards is the fact that there's been this huge surge in demand for the infrastructure for AI. And so that's mostly around co-packaged optics and like high speed data comms. Like this a few months ago, NVIDIA's announcement. Also, Huawei have now, in capability, caught up in part by sacrificing or having a like lower quality electronics, lower quality silicon chips, but compensating for that by the silicon photonic chips. And so this means that there's huge amounts of resources going into improving these processes and looking at how do we get better performance. And then that's led to investment in a lot of kind of novel platforms. So as Richard said, thin film lithium niobate was this fairly niche thing only a few years ago, and now there's probably more than a dozen fabs that offer this as a service, and there's many more materials beyond that. And the reason that that's really interesting for the quantum technologies is often you need to work at wavelengths that aren't in the telecoms bands, or you need low loss switching, which you can't do very well with silicon. And so these new platforms, while they weren't designed for photonics, they just have different characteristics to the like silicon or indium phosphide like existing photonics lines that then we can just take advantage of in the quantum space. And then yeah, as for bottlenecks, have we perfected it? It would seem to be inviting bad fortune if I say yes.
Yeah, I guess so. But I guess I'm wondering if there are any methodologies that you feel like you've kind of, I mean, when you're working on a kind of modeling exercise to try and understand the work ahead, I mean, is there a way that you feel that this, particularly using some of this technology that we've been talking about, I mean, is there a way that you feel more confident about that because of a certain way you're doing it?
Yeah, well, I mean, so we like many startups, like time is your most precious resource. So you look at where the big lead times are, what takes the time, and make sure that you really get that right. So anything that means you have to do a redesign and tape out again is a huge delay. Anything that means we just have to slightly change how we process something, that's fine, and you don't need to worry. So essentially, it's a case of whenever we are doing a tape out, whenever we're sending designs off to be manufactured, we make sure we've thought about, well, how are these going to be packaged? How are we testing all of these? Let's put in some backup designs in case this testing machine is down and we have to test it in a different way. Let's put in some like devices made with a different fabrication model just in case. So like you obviously can't plan for everything, but we really try to plan a lot for if a tape out doesn't work and we don't get anything from it, that's a huge cost. And I guess sort of conversely, one of our key selling points to customers is if you get your tape out wrong, it's going to have a huge cost and a huge delay. So you want to make sure that you've designed everything properly.
Yeah.
So
okay. And just Luca, coming back to you, if I may, in terms of some of the projects that your team is working on, what photonic techniques are proving most useful for you when you're developing applications? Are there any particular things you could highlight from the work you're doing over at the University of Cambridge?
Well, I think so. One of the techniques that we mostly use in my group is related to like the accurate nanometer scale positioning of single emitters. So we have developed in the past a technique that allows us to find the emitters which are generally randomly distributed on a chip, and then we can fully characterize them and then design and fabricate devices which are tailored to the specific emitters under study. So that gives us better performances and increases significantly the yield of the fabrication process. And also it allows us to study how the same emitter works before and after we have fabricated the devices, which means that we can fully characterize how well our device is performing or what are the issues associated with it if it's not performing at its best. Otherwise, I mean, linked to what has been discussed before, talking about lithium niobate and different material systems, something we're working on, and I think is something that can help developing in general the quantum photonics area is hybrid systems. So we know that in order to create a full optical circuit, we need a lot of different elements. So we've been talking about ultra-fast electromodulation, but also in general low losses, and it's difficult to have all these good properties within a single material system. So we are working towards integrating different materials, so 3-5 semiconductors, for instance, for high quality single photon emission, then with a silicon platform for low losses, or lithium niobate for ultra-fast modulation. So these are in general like the technique that we mostly use and that for our research.
Okay. Hybrid systems, any experience of that from anybody else on the panel? Is that something that you routinely use? Annika, Richard, or James? Anybody have any particular insight into that? No, no, okay, fair enough and stuff. So it seems quite useful. So just on that general point then around the actual process of researching and developing the applications that you're working on. I mean, is there a kind of top tip sort of approach to this, in as much as one sort of takeaway thing you've learned from the projects you've been involved in that you would want anybody watching this to understand about how to do it, time frames, things to look out for, that sort of thing? Is there anything that springs to mind about anything that's gone particularly well or badly? I guess the bad experience are just as interesting as the good ones. So Richard, anything to add here about things?
Yeah. I don't want to be on the question of integration of different materials. I think my only challenge would be there's a lot of complexity that comes with lots of different materials.
Yeah.
And maybe the commercial perspective being slightly different from the research one. Like my suggestion would be start super simple. So we started with just one material. We're slowly, carefully adding a second material. I for one aren't that a bigger fan of putting 3-5 materials on chip, because it's another class of material. You've got extra complexity, which comes to more chance that the yield will be low and things like this. So I would say that certainly from our perspective, it's much more about making the system as low risk as possible, making big progress, but continuing to preserve your risk where you can, doing the right things. I actually think that a challenge or the learning has just been about the facility that you use and the choice of partners, because there is this whole spectrum of different facilities you can use, from very, very research grade type facilities. It's good if you're lucky for one device, if a PhD student hasn't messed around with it the morning before you're trying to use the system, through to obviously massively scaled up facility costing millions of dollars of transfer costs and things like this. And Orca's approach actually is to leverage a big supply chain in between. So certain partners for some of the growth stages, etching done in a different facility, And so I think one of the key learnings that I haven't been responsible for, but the team have been very good at doing, is just trying to assess the facility that you're using at the right time and for the right step. And that, in my view, takes a lot of knowledge of the supply chain, of the landscape, of the tools, of the etching, or all the stuff you're trying to do. And is I think the key differentiator between someone doing it as a one-off and versus someone trying to do it as a product, a sort of trustable sort of device and a trustable product, if that makes sense.
Yes, it does. And Annika, I mean, from your perspective, you feel that the choice of partner is a nuanced one, and you have to be approached with caution, or have you had good experiences or bad experiences in terms of sourcing those type of people?
Yeah, absolutely. You have to spend a lot of time to find the right partner. As I said, for us, mainly to look forward as well, to see whether we would be able to scale up together and be able to support in long-term partnerships. And I think on the question on key learnings, and maybe also coming back to the hybrid material choices, I think for us, again, as a startup where time is very critical, it's very important to think about which development steps are absolutely critical and which one can we bridge in between. So what are the steps, or especially in photonic integrated circuit development, that we absolutely have to go through, and which ones can we de-risk someone and test maybe in faster ways or different ways? And that comes down to a lot of assessment of materials, assessment of partners as well, assessment of technical decisions. So we fully understand the entire roadmap, I would say, to say, okay, which steps can we somehow bridge and which ones do we absolutely need to get right. And with, for instance, material integration, I think we are more looking at co-packaging, for example, with combination of electronic ICs, photonic ICs, and then moving down towards 2.5, 3D integration and so on, but that's more on the packaging side.
Yeah.
And again, it's the same questions: which development steps do we absolutely have to do to move forward with certainty and assurance, and which ones can we bridge. And yeah, I think that's the key learning.
Okay, thank you. And James, you and your team are leading an Innovate UK project, which is exploring the use of silicon nitride integrated photonics, which is helping scale quantum computing nationally. Obviously, everybody's obsessing a little bit about supply chains at the moment, quite rightly. There's a lot going on in the world, which is causing some disruption there. I'm wondering if you had a view on the UK supply chain in this space and what further developments could be made to kind of get that working better.
Yeah, so that project was with a handful of partners, including Oxford Ionics, and our role there was in doing design for multiple different wavelengths, but then also coming in on helping to develop that silicon nitride platform. So that was with Cornerstone in Southampton. Later this year, next month, I think, it's available for MPW runs, and hopefully it's a little bit of a jack of all trades platform rather than being super low loss, although we did quite a lot of work to reduce the loss. And so hopefully that's a useful part of the UK supply chain. In general, for R&D, we have quite a flexible supply chain within the UK. There are big kind of chunks of that either missing or hard to access, in that, maybe if you want something on lithium niobate or you want some indium phosphide, like you can actually get that in the UK. It's just not easily and readily available as a service. Yeah. So even at that R&D level, finding how you access the capabilities, even finding out they exist, is a bit of a challenge, even though there's a surprising amount. But what we're kind of really missing is any route to go to volume production. So we're great for prototyping and flexibility, but if you want to make something at volume, you currently don't, that I'm aware of, you don't have an option in the UK other than to develop your own supply chain.
Oh, the light is back on. Yeah. It's interesting you mentioned lithium niobate. I mean, we've had a question come in from somebody about the concern of lithium shortages, particularly, I guess, from electric vehicle batteries, for example. Is that something that's keeping the panel awake at night in terms of supply, particularly in that kind of area, or more generally, if there are supply chain challenges? Luca, what's your take on that issue?
Well, I should say that, I mean, within research, in a university, we don't need a large amount of materials. So it's certainly not something that, directly affects our work, but I assume that like others here who are more like concerned with like products and the ability to deliver might see this as a challenge more than we do in a public university research environment.
I guess that's fair enough. I mean, Richard, I guess you're probably working across the broadest sweep of that industrial sector. I mean, is it something that your kind of clients are talking about a lot in terms of, project development?
I don't think so. I was just trying to calculate in my head how much lithium would be in one battery and how much lithium we need to cover however many wafers we use. So, I mean, we are talking about relatively small amounts of lithium. So don't think I've seen sort of shortages bite yet. The tariff thing, as to state the obvious, the tariff thing is a bigger deal.
Yeah.
Like, we do source wafers from China. Those wafers go to the US. It's sort of, again, to state the obvious, it's sort of not an easy way to do business if overnight the 100% tariffs get applied overnight.
Yeah.
That's a bit of a nasty shock. I think that's probably my bigger worry right now. And semiconductors is, as much as everyone talks about sort of UK supply chain, I'm great supportive of that. I think it's hard to do any of this stuff purely limited to a UK supply chain. So we all move things around between different countries. So those tariffs do bite quite a lot.
Yeah. Annika, I mean, I'm guessing you're obviously working with product from all around the world, are you? Or have you managed to kind of centralize to any degree your kind of supply chain routes?
Yeah, it's a combination. So for scale production, yeah, as we were saying before, I think mainly abroad at the moment. For prototyping, a lot of it is done in the UK. And of course, it's quite interesting to see how often subcontractors react to talking about scaling up on manufacturing quantum technologies. Often they are very hesitant because they admit, oh, we don't have much experience with quantum technologies. This is something new to us. But ultimately, it comes down to the same capabilities they already have with electronics, of course, with photonics, with alignment, with fiber cables, or photonic ICs. If they're packaged, they're just ICs. So you can work together quite a lot and collaborate. And I think we had a lot of upskilling, I would say, where we work with the subcontractors and working together in actually building these quantum technologies and taking away the fear or the hesitation that actually it is just engineering capabilities. And I hope in terms of volume production, that's also something that the UK supply chain will slowly get to, because there are some political challenges that keep us awake, and that could be for volume production. What happens with Taiwan? What happens with material shortages in photonics, in PCB manufacturing, and so on?
Yes. Yeah. No, I mean, there's a couple of themes that have kind of, I suppose, characterized my time in this space. And one has been supply chain, COVID, post-pandemic, kind of supply chains, and now tariffs. It's a sort of omnipresent issue. Another topic that has always dominated all the discussions in whatever area of photonics almost that I get involved with has been this question of AI. And I wanted to ask about network photonic architectures and what role they've played in the development of AI and machine learning algorithms are optimized for these quantum systems. I mean, Richard, any thoughts on how that has played out to date?
Yeah, lots. I'm not sure if this is quite where your question was going, but we certainly see a really interesting space right now in the application of these quantum photonic systems to leading machine learning and AI models. So, I mean, to paint the whole picture, everyone is currently desperately looking, rapidly looking, urgently looking for the first applications of the first quantum computers. And while they're more than likely small, more than likely not error corrected, and all the rest of it, those things will come, but it will take time. No one wants to wait. Everyone wants to know what the first applications are. There is now a lot of good research. There's a lot of bad research. There's also got good research as well, pointing towards machine learning being one of the first applications for smaller scale, still high quality, but smaller scale quantum computers. And I get excited because if you can do anything that impacts the current market for machine learning or AI infrastructure, obviously you're chipping away at a multiple $100 billion market currently monopolized by NVIDIA. You're consuming tons of energy. Any one of our customers will scream at us the problems they've got with current hardware. So if photonics, or more particularly if quantum photonics, can do anything in this space like we think that we can do, doing the same machine learning problems but with fewer NVIDIA chips, less energy, better outcomes, there's a massive market potential. And by the way, I'm very specifically talking about using the photonics as a processor, as a way of partly processing the information. James has already mentioned the really cool stuff on interlinking GPU chips. I'll leave it to James to elaborate a bit on that. But this is the golden era for photonics, right? I've been waiting my whole career to see photonic technologies be actually useful in data centers, in computing, and we've seen the era of photonic computing live and die. Like, didn't amount to much because of the challenges. Silicon's pretty good, electronics is pretty good. This seems to be the era where computing is big enough, scary enough, energy consuming enough that people are actually ready to start adopting this new way of approaching the way we actually do computing, which is really exciting for any one of us, I guess. So I don't know if that answered your question. AI is pretty cool right now, and good to be doing some cool technology towards it.
I'll do a quick straw poll in a minute, but James, the golden age, would you kind of agree? And where is AI playing its place in your work?
I mean, golden age, I don't know, because maybe it gets better. AI is the like single biggest driver of integrated photonics as an industry at the moment. Still, most of the market, most of what's sold is pluggable transceivers. But if you look at where the investment is going, what's being developed, where we think the kind of medium term is, that's in co-packaged optics, which means getting your photonic chip right next to your electronic chip, so that you don't to like minimize the amount of information that's going over copper. And it's for bandwidth and energy consumption. On the compute side, I am fairly ignorant of the space. There's a lot of work in different like photonic computing architectures. None of them that I've seen yet have surpassed what's possible in electronics. It's obviously a hugely difficult problem because you're competing against NVIDIA, who have got limitless resources, and also for photonics, you can't shrink your components down much smaller than the wavelength of the light that you're using. So that means that you don't get Moore's law within photonics. So you have to use other tricks. So whether that's like quantum processing, or whether you find some way of using multiple wavelengths, or you use some other nice property of light, but you have to find some trick to make it work. And there've been lots of like nice demonstrations. Nothing's got there yet, but this huge kind of demand and the ridiculous energy consumption has meant that a lot of approaches to this have got the funding to go and have a shot at it, and only some of them need to work, and then maybe it's golden age.
Yeah, game changer on the horizon. I mean, Luca, with your teams, is AI being used on your kind of projects, at the moment?
Yes, I would say, I mean, without projecting into the future, I would say that what I see as a very powerful resource in AI is in design of photonic structures right now. So we can use all these machine learning approaches to either completely design new structures with like counterintuitive approaches, but also, I mean, in general, see if we can, for instance, extract some characteristics of like materials or elements without having to do a full measurement or experiment on characterization. So try to get like some sort of like rough ideas already from like previously collected data on what we can predict in new devices, or just design novel structures in a faster, more efficient way than what we could do before using AI approaches, for instance.
Okay. No. And Annika, I mean, in terms of your work, I mean, I'm guessing AI has a place. Are you using it at the moment?
I think we approach it from both ways, I would say. So yeah, use it in some of design tasks, be that translating PDKs from one to another platform, something like this. But for us, we observe it because many machine learning models, especially generative models, rely ultimately on probabilistic approaches.
Yeah.
And their performance could be enhanced with specific probabilistic hardware, let's say. So I think that's our main focus. So if we look at dedicated hardware to accelerate specific probabilistic tasks, they would require true randomness. And that's something we look at integrating these our photonic randomness sources into the compute procedures in the hardware to enable these machine learning models to be run more efficiently and effectively.
Yeah. And presumably that has a place to play in QRNG, quantum random number generator technology, which is obviously driving digital security ultimately. But I mean, how are those? Is that where the value is being created through AI, or is it just basic, more general photonic sources in terms of that? How is it helping advance that digital security?
Yeah, I think ultimately random processes are the very fundamental building block. And that could be for cybersecurity for key generation, or it could be for probabilistic computing approaches. And when we look at digital security, our cybersecurity, we ultimately provide this fundamental building block of random numbers for key generation. And all the encryption protocols are just layers on top that ultimately rely on this building block. And I think where we use photonics is really the underlying or the underpinning principle of quantum mechanics, that you cannot predict the outcome of a system until you measure it. The classic Schrödinger cat example. And we leverage this unpredictability of the quantum processes to generate these random numbers. And because we use photons, which are generated in large quantities by lasers, of course, and we use the phenomenon of photons hitting beam splitters. So a beam splitter just means a photon gets either reflected or transmitted. And this specific process or this path a photon chooses is inherently indeterministic. And ultimately, it's a very simple but very fundamentally random process. And that allows us to generate randomness at very high speed and very reliable. And I think it's not only this fundamentally random process that quantum mechanics enables us to do, but we also have a way of actually quantifiably measure, in this case, the width of the entropy distribution or the behavior of the photons, really. So we understand what is the amount of randomness or the amount of entropy that we can generate in our system. And that's something that only quantum photonic devices can help us with, because that means we can actually measure the amount of randomness we have, and we can determine the minimum entropy level, it's called, based on the quantum process, and distill it from any electronic noise or thermal noise. And that's a very powerful assurance in cybersecurity or digital security, because that metric of how much entropy you have in each sample is an additional security factor. If you, for example, want to generate a 256-bit key, you need to know how much entropy is in there to have the assurance that it's actually a truly random encryption key, and you don't rely on any assumptions from statistical testing or from pre-measurements or something, because you get this measurement of entropy in every sample, which ultimately stems from the photonic and from the quantum nature of photonics.
Okay, no, thank you. I mean, it's hard to imagine you being able to develop the work that you're doing without this kind of technology being in place, right? I mean, it feels, you know, something which you can now do relatively quickly and easily. You know, 3, 4, 5 years ago, almost certainly wouldn't have been the case. So it's, you know, it is real cutting edge stuff. Our audience is pushing us back into the packaging question, and again, Richard, you were saying you weren't that convinced by the UK's ultimate capability in this space, but the question that's come in is, how do you view the UK's packaging capabilities? Are they competitive, or do you look more towards EU, like Fix and Linux, to address this aspect of the production line? Obviously, some people out there desperately trying to kind of fix this conundrum. Richard, I'll start with you, if I may. You know, what can the UK do to make this easier, if anything?
This is unfortunately going to be only our experience, and I'm happy to hear if anyone else wants to get in touch with other. Our experience of trying to package chips in the UK has not been very successful, and we've just had, maybe it's the performance that we're expecting, or something like that. But we currently package our systems, our chips in the US, because so far we haven't had any successes with a UK vendor, which has been a little disappointing. I'm sure people will want to reach out to me and suggest otherwise, and happy to hear of alternatives. In terms of general challenges, I think there is a big one of volume. Like, it's a big supply chain, and expecting all of that to be done in the UK is just, is there enough capacity in the UK to see the number of chips go through to be good at everything? And so my slightly controversial thing that I sometimes say to UK government is, by the way, for many companies, it's fine if everything's not in the UK. There's certain things we just accept aren't done in the UK. I don't know if packaging is a good example. In my experience, it's not something we do particularly well. But I think the UK should be sort of picking picking things that we think we could be competitive in and not worrying about everything. And the only community I ever hear about who wants everything wholly UK and maybe defence, but you know, that's not necessarily a commercially guided answer. So I'm happy to hear of others' experiences. In ours, packaging is not something in particular I've had experience being done well in the UK.
Okay, James, Annika, and possibly Luca as well. Any thoughts? Anybody you've come across that is doing it well, or you've had a good experience, James?
Yes, I mean, I wouldn't claim to be an expert on packaging. We have done some work in design for packaging, and this was with Alta and with Sanko, a fiber components company. Problem we were trying to tackle was that people tend to only consider packaging at the last minute. So they'll make a chip and then go to a packaging house and say, can you package this? And you either need to then redesign your chip or do a lot of customization for your packaging. And then typically at the moment, your coupling on and off chip is quite high loss. So we have some ongoing work also with Alta to try and bring that down. But as a standard today, it's quite high loss. So you can spend tons of time optimizing the hell out of every little design on your chip, but then if you lose half your light getting it off the chip, well, that's a big problem. In terms of volume, I'm not aware that we have capability to do things at volume in the UK. I don't know whether that's a problem. I know that Alta will support if you get some process with them and then want to take it to high volume, but that's different to just knowing if I design my chip like this, I can get it packaged at high volume. And I'm not aware that we have anything like that in the
Okay. Annika, what thoughts on this?
Yeah, we have packaged prototypes in the UK, but as soon as we're looking at higher volumes, we looked into the EU or further east as well.
Okay. And when you're doing just the prototypes, is that because of the geographical proximity or because you feel that the actual prototype work is of a particular, expertise or cost perhaps?
I think it's both. So one is, of course, proximity. It speeds up the process if you have your picks and you can get them packaged and tested very quickly. And also to trial different packaging houses. So usually during the prototyping phase, we work with multiple partners to understand, different capabilities and collaborations. But yeah,
Okay.
for volume production, as James and Richard were already saying, we were then also looking abroad.
Yeah. And Luca, I guess from an academic perspective, they're often quite stringent kind of conventions around where you go for different types of work and partnerships. What's your experience in this space?
Yeah, so we have been looking at commercializing some of our photonic devices, and I have to say that for the packaging as well, we have been looking at European collaborators. And I mean, from our perspective, I mean, we're not looking at very large volumes, but in any case, the main difference if you go abroad is mostly like funding restrictions or like what kind of proposals you would submit. But also, I mean, also being, I mean, if it was in the UK, then it would be easier to go and visit maybe and just have a quick discussion and see, I mean, follow how the packaging is developed more closely than if you are relying on somebody who's elsewhere.
Yep. So I think the answer then for that person that sent in the question is basically it's good examples of prototyping. Proximity obviously is a practical consideration, perhaps scaling everybody's in the same place on this so that there's not necessarily a good or quick answer on that one. We are nearly out of time. I'm going to ask another final question of our four speakers today, if I may. And it's a general one again. It's a crystal ball time. And it's how do you see quantum photonics continuing to develop in the coming years across the industries that it's already perhaps got a foothold in? Maybe if you could sort of keep it down to one insight or one prediction, if I may, and I promise not to come back and necessarily challenge you on it 2 or 3 years hence. But James, I'll start with you, if I may.
So I think driven both by quantum technologies and other integrated photonics applications beyond datacoms, so a lot in the sensing space, that we will see a continuing development of different material processes. So photonics won't just be on silicon or indium phosphide. I think we'll see a like hugely a huge diverse array of different materials and processes and different like wavelengths that we use for that, just guided by the needs of sensing and quantum applications. Coming after all of the AI stuff, though.
Okay, thank you. Annika?
Yeah, I think the goal for us is, of course, entering computing, be that in cybersecurity or in solving computing challenges that are unfeasible to solve thus far. Yeah, that's the the main goal, to get quantum photonics into these markets.
Okay.
I think that would be the development we would like to see.
Okay, fair enough. Luca, I'll come to you next, if I may.
So I think that, yeah, I mean, something where I see the potential for major breakthroughs is in imaging and biomedical applications as well. So it's something we haven't really gone into much of a detail today, but I think that if we manage to have like higher sensitivities, low photon fluxes used to image and improve capabilities there, then it could bring very important breakthroughs in that area.
Okay, thank you. And Richard, last but not least.
Yeah, thank you. You asked for one. I'm going to quickly do two.
Enough.
One very quick one is commercial quantum advantage. I mean, we've talked a little bit about how powerful quantum systems will be right on the cusp of quantum outperforming classical, and that will be a game changer for the quantum industry in computing, but also sensing and everything else we're talking about. We're right on the cusp of seeing quantum being useful. But the second answer I'd give is slightly more technical, though we talked a bit about the new materials being used for integrated photonics. It is actually the case that I don't think those new materials outperform the existing, and we're talking about beating silicon heaters, like quite old school stuff like that. But right now, there are not just one company, but many companies tracking the integration of new, super exciting new materials, lithium niobate, all the others, with these classical existing materials. And in the next year, those will start outperforming, and you will start to see really, really fast, really low loss devices. So on the material side, there's a little bit of activity happening, and it's just about to start competing with the things that we've been using for the last 20 years, which is really cool.
Okay. Thank you. Well, that sounds very much like a watch this space kind of message. So we will almost certainly want to revisit this topic. It's one of the ones that comes up over and over again in terms of things that kind of our audience are interested in. So thank you. We have run out of time for the session. So I have a few things just quickly to say. The online panel discussion will remain accessible on the Electro-Optics website. That's electroopticsnospace.com, and it will eventually turn up on our YouTube channel. We'll also be creating an online article about the discussion today, and we'll be publishing that in due course. So please spread the word among your colleagues if you've enjoyed the presentation. I have to say a huge thank you to our presenters, James, Annika, Richard and Luca, and of course the Europe Science production team working away in the background. And obviously, time is precious, so big thank you to everyone out there who has taken the time to watch today. Please keep an eye out for further sessions. We have a few coming up. We've got the shortlisted entrants for the Photonics Frontiers Award 2025, appearing in 3 broadcasts. There's 18 of them, and they'll be running at the end of May across 2 days. Thank you to everybody again for your time today. Really insightful discussion, some interesting takeaways there, and certainly a lot of development in the space. So we will want to come back to this and revisit where things have ended up. Thanks again for your time. Hope to see you again soon. Thank you again to our speakers. You have been great. Thanks very much. Bye-bye.
Thank you. Bye.
Thank you.
Thanks all.